Welcome to The Explainer. Today, we're diving into a genuinely fascinating piece of scientific literature called CO2 Reduction to Methanol in the Liquid Phase, a Review. This paper, published in Chem by researchers from Washington State University and the China University of Petroleum, takes on one of the absolute biggest scientific challenges we're facing right now. We're going to look at some incredible chemical innovations that could literally let us pull carbon dioxide right out of the air and transform it into a highly valuable chemical. Now, I know it's a dense paper, but stick with me, because by the end of this explainer, you'll understand exactly how this chemical magic actually works.
So, what if we could recycle the sky? Seriously, think about it. For decades now, we've basically looked at atmospheric carbon dioxide as just trash, an invisible problem just piling up above us. But what if we completely flip that perspective? What if we grabbed that CO2 and used it as this infinite airborne quarry? Well, this paper proposes exactly that, taking atmospheric CO2 and turning it from this massive environmental liability into a tangible, high-value industrial resource.
And when I say high value, I mean massive scale. 70 million. That's how many tons of methanol the world demands every single year. 70 million tons. Right now, we're meeting that giant demand mostly with fossil fuels. But if we can efficiently synthesize that methanol using the CO2 that's already floating around in our atmosphere, we aren't just solving a climate problem, we're tapping into a gigantic, pre-existing global market. I mean, the opportunity here is just huge.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the carbon dilemma, then look at methanol, a liquid solution. Next, the liquid phase advantage, followed by dissolved catalysts in action and solid catalysts for industry. Finally, we'll wrap up with closing the carbon loop.
All right, Section 1, the carbon dilemma, the scientific context.
To really appreciate the chemical solutions in this review, we've got to ground ourselves in the macro problem driving all this research. The paper kicks off by highlighting the rising CO2 concentrations in our atmosphere. The authors report that this rise is linked to an enhanced greenhouse effect, which, as the scientific consensus points out, is a primary driver for extreme weather and climate change. Because dumping all this CO2 has such negative impacts, the paper stresses that we absolutely must focus on CCU, carbon capture and utilization. You know, it's just not enough to trap CO2 and bury it somewhere. We actually need to utilize it. We need to loop it right back into the economic cycle.
Moving on to Section 2, methanol, a liquid solution.
Look, if we're going to go through the trouble of capturing millions of tons of CO2, we better convert it into something super useful, right? Enter methanol. It's an absolute game changer. It's a top 5 global commodity chemical. It acts as the fundamental precursor, which basically means it's the raw building block for everyday stuff. Plastics, the adhesives in your plywood, paints, you name it. But beyond just making things, methanol is a huge player in the future of green energy. It acts as this high-density hydrogen storage carrier, which makes it way easier to store and transport than pure hydrogen gas. Plus, it can be used as a direct fuel for mild-temperature fuel cells. It is just incredibly versatile.
Okay, Section 3, the liquid phase advantage. So, how do we actually pull this off? How do we take a stubbornly locked gas and turn it into a versatile liquid? Well, it all comes down to catalysts. Basically, a catalyst is a substance that speeds up a chemical reaction without getting permanently changed itself. Think of the CO2 molecule like a locked box. It's highly stable, it really doesn't want to react with anything. A catalyst is essentially a carefully designed key that forces that lock open so we can rearrange the contents into methanol.
Now, traditionally, this whole process has been done in the gas phase, but that requires extreme conditions. We're talking temperatures over 200 degrees Celsius and insane pressures over 50 bar. That takes a massive amount of energy, which makes it expensive and, frankly, not very environmentally friendly. But the big innovation explored in this review is the liquid phase. By doing this in liquid solvents, the reaction happens at much milder temperatures. And what's even cooler is that it seamlessly integrates CO2 capture using chemicals called amines. When CO2 gets absorbed by these liquid amines, its chemical bonds are physically altered. The amines essentially soften the lock on the CO2 molecule. That makes the catalyst job way easier and saves a huge amount of energy.
Inside this liquid phase, we generally use 2 types of catalysts, homogeneous and heterogeneous. Let's use a quick analogy here. Think of a homogeneous catalyst like sugar dissolved in a cup of tea. It mixes perfectly, reaches every single part of the liquid, so it's super efficient at converting CO2. But just like that dissolved sugar, it's incredibly hard to separate back out when you're done. Now, a heterogeneous catalyst is more like a tea bag. It doesn't dissolve, it might not mix as perfectly as the sugar, but when the reaction is over, you just pull the tea bag out. You can reuse it and easily separate out your product. Because it's so reusable, heterogeneous catalysts have massive industrial potential.
All right, Section 4, Dissolved catalysts in action.
Let's zoom in on those sugar catalysts first, the homogeneous ones. The paper reviews this really fascinating array of metal complexes that basically act like tiny teams of microscopic workers. Ruthenium is the absolute high-performing workhorse of the group. It delivers these massive turnover numbers, which is just a fancy chemist way of saying it can convert a huge amount of CO2 molecules before breaking down. Then you have manganese, which the paper highlights as a multi-step expert, elegantly guiding the CO2 through sequential changes in a single pot. And then there's iron. Now, iron might not be quite as ruthlessly efficient as ruthenium, but it is super abundant in the Earth's crust, which makes it a cheap, completely Earth-friendly alternative to those rare precious metals.
And this brilliantly illustrates the step-by-step loop these homogeneous catalysts guide the CO2 through. First off, the CO2 reacts with the liquid amine solvent, trapping it and locking it right in place. Second, it gets reduced into a compound called ammonium formate. Next comes dehydration, pulling out the water to create an intermediate stage. And finally, through hydrogenolysis, hydrogen cleaves the molecule, releasing pure methanol and freeing up that amine solvent to start the whole cycle over again. It's just a beautiful, elegant chemical loop.
Moving on to Section 5, solid catalysts for industry.
So, as we talked about earlier, separating out those dissolved sugar catalysts is a real headache. If we're talking large-scale industrial manufacturing, we really need solid catalysts, those heterogeneous tea bags that make the process commercially viable. And when it comes to solid catalysts, copper is king. Specifically, copper-zinc oxide combos are the industrial standard. But the paper details this awesome liquid phase twist. By running the reaction in an alcohol solvent like ethanol, the alcohol actually acts as a co-catalyst. It teams up with the solid copper to drive the reaction incredibly efficiently and at way lower temperatures than you could ever get in a traditional gas phase system.
Let's see how this builds into just an incredible leap in productivity. Now, there is a catch to the liquid phase. Water forms as a byproduct during the reaction. And unfortunately, water is pretty toxic to these copper catalysts. It essentially poisons them and slows the whole operation down. Your standard copper-zinc oxide setup might yield about 8.2 grams of methanol per kilogram per hour. But researchers found that if you simply add a molecular sieve, which is just a material designed to soak up that pesky byproduct water as it forms, the productivity literally skyrockets to 54.4. Just by keeping the environment dry, methanol production gets a massive boost. And finally, Section 6, closing the carbon loop.
We've spent some time in the microchemistry weeds, so let's zoom back out to the big picture and this incredible future of green chemistry that the paper envisions. So the crucial point is, as the authors perfectly summarize, converting CO2 into value-added chemicals or liquid fuels is an ideal way of closing the carbon cycle. By capturing CO2 right at its source, like a power plant exhaust, absorbing it into a liquid amine, and then using these advanced catalysts to convert it directly into methanol in situ, we stop treating carbon dioxide like trash. We actually create a true sustainable loop where the carbon is constantly being repurposed.
I want to leave you with this thought as we wrap up today's explainer. When you look at the progress we've covered today, from rare earth homogeneous chemistry to these highly scalable water-absorbing copper catalysts, it feels like we're standing right on the precipice of a chemical revolution. What if our biggest waste product truly becomes our greatest resource? Just imagine a world powered and built by the very air we're trying to clean. Thanks so much for learning with us today.